Welcome to Semester 4 Mathematics. Today, we are diving into the fascinating world of sequences and series of functions. Imagine building a complex synthesizer sound by layering simple waves. We will explore how adding infinitely many mathematical rules can either create a beautiful stable function or chaotic noise. Let us begin our journey into convergence. Now that we have introduced the topic, let us understand what a series of functions actually is. Think of a music producer creating a new synthesizer sound. You start with a basic hum, add a higher tone, then another. Each sound wave is a mathematical function. When you add an infinite number of these waves together, you create a series of functions. The big question we must answer is, does this infinite combination result in a clear, stable musical note, or does it become infinitely loud, chaotic noise? If the combined sound eventually settles down into a stable, predictable wave as you keep adding layers, we say the series converges. To make sense of this infinite addition, we need a mathematical way to write it down. This formula represents the exact instruction to add our functions together. The capital S of x is the final total function we get after adding everything. The sigma symbol tells us to sum things up, starting from n equals 1 all the way to infinity. The term f sub n of x represents the individual separate functions we are layering one by one. As the index n increases, we move further down our infinite list of functions, adding each new one to our total. If the individual functions grow too fast, the total might explode. But if they shrink appropriately, we might find a stable result. Since we cannot physically add forever, we use a clever workaround. We define a partial sum, which is simply a running total of the first few functions, stopping at a specific number n. By studying this finite sum, we avoid the impossible task of adding forever. Instead, we look at the trend of this running total as n gets larger. This brings us to the mathematical heart of convergence, the limit. The limit asks what destination the running total is heading towards as the number of terms approaches infinity. If this limit exists and equals a specific function, the series converges. If the running total blows up or oscillates wildly, the limit does not exist and the series diverges. Now that we have defined convergence, we must introduce a critical distinction: pointwise versus uniform convergence. Why does this matter? Because how a series settles down is just as important as whether it settles down. Pointwise convergence means that if you pick one specific fixed input value, the running total at that exact spot eventually settles to a final answer. However, different spots on the graph might take vastly different amounts of time to settle down. Uniform convergence is a much stronger, better condition. It means the entire running total graph settles down to the final graph at the exact same speed, everywhere, all at once. Think of pointwise convergence like fixing a leaky roof one specific drop at a time, whereas uniform convergence is like throwing a giant, perfect tarp over the entire roof in one smooth motion. Before we move on to more abstract ideas, let us see this with a concrete example. We want to find the sum of a classic series where each individual function is simply the input variable raised to a power. We are given that the nth term is x to the power of n starting from n equals 0. Our goal is to find out what this infinite addition equals and for what values of x it actually works. To solve this, we first write out the running total, which is the partial sum. We start with x to the power of 0, which is 1, and keep adding higher powers of x until we reach x to the power of n. This represents the physical act of adding the first few layers of our mathematical structure. Continuing with our running total, we notice a helpful pattern. Because this specific addition follows the pattern of a geometric progression where each term is multiplied by x to get the next, we do not have to leave it as a long string of additions. We can use the standard algebra formula for the sum of a finite geometric series to collapse it into a compact fraction. This gives us 1 minus x to the power of n plus 1, all divided by 1 minus x. We must note that this formula is valid as long as x is not exactly equal to 1, because plugging in 1 would cause a division by 0, which is mathematically undefined. Now we apply the limit to our compact fraction to see what happens as we add an infinite number of terms. The only part of this fraction that changes as n grows larger is the x to the power of n plus 1 term in the numerator. If we restrict our input x to be a fraction strictly between -1 and +1, then multiplying that fraction by itself infinitely many times makes it shrink to 0. When that term vanishes, we are left with our final answer, the function 1 divided by 1 minus x. This means the infinite series of polynomials perfectly converges to this simple rational function, but only for inputs in that specific safe range. To truly grasp what we just calculated, let us look at it visually. Here we see a graph showing the partial sums of our geometric series. The horizontal axis represents our input x and the vertical axis is the output. The solid black curve is our final target function, 1 divided by 1 minus x. The dashed lines represent our running totals. The blue line is just the first two terms, the red line adds another, and the green line includes up to the fifth power. Notice how between x equals -1 and +1, the dashed lines hug the solid black curve tighter and tighter as we add more terms. This visualizes the series converging to the final function within that specific safe range. Now that we have seen a basic example, we need a way to handle more complicated functions. To prove uniform convergence, mathematicians use a powerful technique called bounding. Why do we need this? Because checking every single point on a graph is impossible. Instead, the strategy is to find the absolute worst case scenario, meaning the maximum possible size for our function regardless of what the input x is. By doing this, we create a guaranteed upper limit or ceiling. If we can show that an infinite series made entirely of these worst-case maximum values still converges to a finite number, then our original series of functions must be trapped beneath it. Therefore, it is forced to converge uniformly everywhere. Let us apply this bounding strategy to a real problem. We need to determine if the infinite series of the functions given by sine of n times x divided by n squared converges uniformly for all possible real numbers x. This is a more complex series because it involves both trigonometry and fractions. To begin our proof, we want to find that worst-case ceiling. We start by taking the absolute value of our function to look strictly at its size, ignoring whether it is positive or negative. This sets us up to find the maximum possible value this fraction can ever reach. Continuing with our bounding test, we look at the numerator of our fraction. We know from basic trigonometry that the sine function, sine of n times x, can never be larger than 1 or smaller than -1, no matter what values of n or x we plug in. Therefore, the absolute biggest the numerator can ever be is exactly 1. This is a fantastic simplification. It allows us to replace the complicated, oscillating sine term with the number 1. By doing this, we have successfully created a guaranteed upper limit or ceiling for our function, which is simply 1 divided by n squared. For the final step of our proof, we look at the infinite series formed by our worst-case ceiling values. This gives us the sum of 1 over n squared. This is a well-known mathematical series called a p-series, specifically with the power p equals 2. Because the power 2 is strictly greater than 1, mathematical rules for p-series guarantee that this sum converges to a finite specific number, which happens to be pi squared over 6. Because the series of our worst case maximums converges to a finite number, our original trigonometric series is trapped beneath it. This gives us our final result. The original series is forced to converge uniformly for every single value of x. So we have proven that uniform convergence holds for our series. This brings us to an important question. Why does this matter in the real world? The convergence of a series of functions is the absolute foundation of signal processing, telecommunications, and quantum mechanics. For instance, when your phone transmits your voice, it breaks down the complex sound wave into an infinite series of simple sine and cosine waves, known as a Fourier series. We need to know that when the receiver adds all those infinite waves back together, the series converges exactly to your original voice without blowing up into static. Furthermore, we specifically need uniform convergence if we want to perform calculus on these signals. If a series only converges pointwise, trying to take its derivative can result in mathematical garbage, completely ruining the signal analysis. We have covered a lot of ground today, so let us review the most important ideas. First, a series of functions is simply an infinite addition of mathematical rules, and we study it by looking at the limit of its partial sums. Second, we learned the crucial difference between pointwise and uniform convergence. While pointwise convergence means the sum works at isolated spots, uniform convergence is the gold standard, ensuring the entire graph settles down together. Finally, this stronger uniform condition is what allows us to confidently apply calculus to complex real-world systems like audio signals. You now have a solid foundation in the convergence of series of functions. Keep practicing and the math will continue to unfold beautifully.